Okay, let's talk about some torque applications. We're going to use torque to illustrate three different types of examples. First, we're going to talk about balancing masses, then we're going to talk about levers, and then we're going to talk about a screwdriver handle. Okay, so here we have a balance with two masses attached to it. Mass A has a mass of 0.67 kilograms and is located 0.23 meters from the pivot point. Block B has a mass of 1.2 kilograms. Where should it be located so that the balance beam is perfectly horizontal and is not moving? Is this a translational motion or a rotational motion problem? Pause the video now if you want to go ahead and calculate this. Okay, so let's go ahead and take a look. Actually, I'm going to go ahead and tell you. It doesn't tell me on the next slide. Okay, so if you have a block that is 0.67 kilograms and it's located 0.23 from the pivot point, that gives me a torque of about 0.15. Okay, I want mass B to have the same torque, so I need to find out how far away it is. So what I'm going to do is I'm going to go ahead and divide my torque by the 1.2 kilograms and see what distance it has to be. And I get about 0.13 meters. So it needs to be 0.13 meters away from the pivot point in order for the torque on A to be equal in magnitude to the torque on B. Notice that the torque on A, if you look at how it's moving, it's going to make this whole system rotate counterclockwise, which is a positive torque. If you look at B, if we were to just have B move it, we're going to see that it will make this move in a clockwise direction. So this will move counterclockwise, which is a negative torque, or positive torque, sorry. This is going to cause a rotation to be this way, which is going to cause a negative torque. Negative torque plus a positive torque should give you zero torque if this is not moving. Okay, so let's look at a seesaw. Here's an artistic hint. Oh, they are going to tell us, okay. The two boys on the left represent mass A, and the two slightly larger boys on the right represent mass B. Okay, so in this rotation motion problem, in order to have the beam not rotate, the sum of the torques must equal 0, which we've already covered. And again, like I showed you, substituting in the equations and solving for the torque, we end up with a distance of about 0.13 meters. Note the signs that mass A is rotating counterclockwise, mass B is rotating clockwise. That's a negative torque. So when we add the two torques together, we should get 0. Again, many elementary school students already know this, right? If you remember being little and being on a seesaw, if you had a really heavy kid, he went closer to the center, and if you had a really light kid, you put him all the way on the end in order to balance the students. Just like that. Okay, so John and Sally are sitting on the opposite sides of a seesaw, both of them 5.0 meters distant from the fulcrum. Sally has a mass of 45 kilograms. What is the gravitational force on John if the seesaw is not moving? And in this example, we're going to use 10 meters per second squared as the acceleration due to gravity. Okay, so go ahead and solve the problem now. Pause the video if you need to. Okay, so let's see, you should have gotten 450 newtons. Okay, and how did we get that? Well, they're both 5 meters apart. Sally's mass is 45 kilograms. It's not moving. Therefore, John must also have a mass of 45 kilograms. But they didn't ask for the mass. They asked for the gravitational force. In this case, we multiply the 45 kilograms times 10 meters per second squared, and that gives us 450 newtons. And the answer is A. A student wants to balance two masses of 2.0 kilograms and 0.500 kilograms on a meter stick. The 0.500 kilogram mass is 0.500 meters from the fulcrum in the middle of the meter stick. How far away should she put the 2.00 kilogram mass from the fulcrum? Go ahead and pause now and solve this problem. Okay, so let's see if we have the right answer. The correct answer is D, 0.125 meters. You're going to solve this just like the example. We know that both of the masses are going to be on either side. We know that the 0.500 kilogram mass is located 0.500 meters away. So your final equation should be the mass of the 0.500 kilogram times the 0.500 meters divided by the 2 kilograms should give us the distance of 0.125 meters. Now notice here I did not use mass and not force. But if you remember, both of these have to be multiplied by 10 meters per second squared. So the acceleration due to gravity cancels out on both sides, just like the sine theta does. Sally wants to lift a rock of 105 kilograms off of the ground. She has a 3.00 meter long metal bar. She positions the bar on a fulcrum, actually it's a thick log, which is 1 meter away from the rock, and wedges it under the rock. She can exert a force of 612 newtons with her arms. How far away from the fulcrum should she exert this force to move the rock? And again, please use G is equal to 10 meters per second squared for this problem. Go ahead and pause the video now. Okay, solving this the same way as all the other problems, you should have gotten 1.7 meters. Sally wants to lift a large rock off the ground. She has a 3.00 meter long metal bar. She positions the bar on a fulcrum, and again it's the thick tree log 1 meter away from the rock, and wedges it under the rock. She pushes on the bar at a distance of 1.8 meters away from the fulcrum and starts moving the rock. Joe then comes by and he wants to try moving the rock, but he is not as strong as Sally. What should he do? There's actually 2 answers that are correct. So go ahead and pause the video if you need to and select them now. Okay, so here are your answers. He should push the bar farther from the fulcrum, and C, move the fulcrum closer to the rock. Okay, those are his 2 options. Okay, so let's go ahead and talk about levers in the next video.